Engage. I mean, who doesn't love that sound? It's the dream, isn't it? Humanity just skipping across the galaxy.
It really is the ultimate sci-fi promise.
But then, bam, reality hits hard. You look at the distances involved, and it's just brutal.
Yeah.
Think about Voyager 1. It's the fastest thing we've ever sent out there, flying for decades.
And it would still take it, what, 75,000 years just to get to Proxima Centauri, our closest neighbor?
Exactly, 75,000 years. It makes the cosmos feel less like an ocean to explore and more like a prison. The bars are just sheer distance.
Well, trying to break that cosmic speed limit isn't just about better rockets. We're up against something fundamental.
You mean Einstein?
Precisely. His 1905 theory, special relativity, it's pretty uncompromising.
It basically says nothing with mass can hit the speed of light.
Correct. Because the energy required becomes infinite. It's not a tech problem we can just solve later. It's woven into the fabric of physics. It's a hard wall.
Okay, so, wall. Infinite energy needed. Seems like game over. But, and this is why we're diving into this today, based on these sources, what if Einstein himself gave us a potential out? Like a loophole?
He sort of did, yeah. 10 years later, 1915, with his theory of general relativity.
The other one, the gravity one. We always hear that bowling ball and a trampoline analogy for that.
Right, and, our sources rightly point out that analogy is, well, it's not great. It's misleading.
How so?
It makes you think of space bending down into some other dimension, and it completely forgets about time. Plus, it makes space-time seem static.
Okay, so if the trampoline is out, what's a better way to think about it? Especially for warp drives.
Think of space-time as a river. It's dynamic, it flows, it can be warped and churned. Gravity is just how mass affects that flow.
A river. Okay, I can picture that.
And here's the crucial bit, the aha moment for warp. Special relativity stops you moving through the river faster than light.
Right, the speed limit within the river.
But general relativity, it says the river itself can flow however it wants. The fabric of space-time isn't bound by that same limit.
And we've seen that, right? The Big Bang of the universe expanded way faster than light initially.
Exactly. So the fabric can break the speed limit. That's the loophole. You don't move through space faster than light. You move the space itself, carrying you with it.
Like a surfer on a wave. Or that fly in the car analogy.
Yeah, it's a great one. That's the ship. It just lands on the car seat. It's stationary relative to the seat, totally obeying special relativity.
But the car?
The car, the local space-time bubble around the fly, can be zooming down the highway at incredible speed relative to the ground, the wider universe.
Okay, concept clear. But how do you actually do that? Build the car. That leads us to Miguel Alcubierre, right? 1994.
Yep, Miguel Alcubierre, a theoretical physicist in Mexico and apparently a big Star Trek fan, which probably helped.
I bet.
He took that general relativity loophole and actually wrote down the math for it, the Alcubierre metric, a formal mathematical blueprint for a warp drive that works, at least on paper, within Einstein's laws.
So how does his blueprint work? What's the mechanism?
It's elegant, conceptually. You create this warp bubble around your ship, and the trick is how you manipulate space-time around the bubble.
Okay.
You need to contract space-time, like really squish it, in front of the ship, pulling your destination closer.
Right.
And behind the ship, you need to do the opposite. Expand space-time dramatically, pushing you forward.
So you're creating a wave, basically, and this ship just rides it.
Exactly like riding a wave. And the really cool part, inside the bubble, space-time is engineered to be perfectly flat, meaning the passengers feel absolutely nothing.
Yeah.
Zero acceleration, 0 g. You could be, globally speaking, accelerating at 1,000 c.
1,000 times the speed of light?
Yeah, hypothetically.
Yeah.
But inside, your coffee stays perfectly still in its cup. You're just floating comfortably.
Okay, that sounds perfect. Too perfect. What's the catch? Because there's always a catch.
Oh, there are catches. Big ones. As soon as people looked at Alcubierre's math, two massive problems jumped out.
Problem number one.
The energy, the sheer amount needed was just mind-boggling. Initial calculations were talking about the mass energy equivalent of Jupiter.
Jupiter.
Some estimates went even higher, like
Yeah.
the mass of the entire observable universe.
Right, okay, so not exactly practical. You can't just pop down to the store for a Jupiter's worth of energy.
Not easily, no. But honestly, that energy problem might be solvable someday. The second problem is way deeper, more fundamental.
Which is?
The type of energy, or rather matter, required. It needs what physicists call exotic matter.
Exotic matter. Sounds intriguing, but probably bad.
It's basically stuff with negative mass or negative energy density. Think about it. Normal matter, Normal energy, it pulls space-time inward. That's gravity.
Right. Makes dents in the space-time river.
Exactly. But to make the warp bubble expand space-time behind the ship, you need the opposite. You need stuff that repels space-time. Anti-gravity, essentially.
Negative energy density. Does that even exist?
Well, that's the problem. It violates some really basic assumptions in physics, what we call energy conditions. These basically say energy density has to be positive. So this key ingredient,
Yeah.
it's like needing unobtainium. It shouldn't exist according to standard physics.
But hang on, don't our sources mention something from the quantum world? The Casimir effect. Doesn't that involve negative energy?
Yes, the Casimir effect. It's real, it's measurable. You take two metal plates, put them incredibly close together in a vacuum,
Yeah.
and the quantum fluctuations between the plates are suppressed. There's less energy between them than in the vacuum outside. That tiny region does have negative energy density relative to the surroundings.
So it is real. A little bit of anti-gravity.
A tiny, tiny bit, yes. It proves the concept isn't completely forbidden by nature, but, and it's a huge but.
The tragic catch, as the scientists call it.
Right. It only works on the nanoscale. And crucially, the total energy of the whole system, plates and all, is still positive. You can't somehow scoop out just the negative bits.
So no way to harvest the Jupiter's worth we need.
Absolutely no known way. It's a fascinating quantum effect, but it doesn't give us a path to building a warp drive. Not even close.
Okay, so for ages, the Alcubierre Drive was stuck in this cool idea but impossible category. Exotic matter needed insane energy.
Pretty much, yeah. Fun for theorists, but not seen as practical engineering.
But physicists don't give up easily, do they? People started chipping away at that energy problem. I saw Chris Van Den Broek got it down from Jupiter mass to a few solar masses in '99.
He did, yeah, by tweaking the bubble geometry. Still way beyond us, but moving in the right direction, at least mathematically.
Then things got really interesting around 2012 with Dr. Harold Sonny White at NASA EagleWorks.
Sonny White. Yeah, he made quite a splash. He figured if you change the warp bubble shape again, not a sphere, but more like a thick donut or torus.
The donut shape.
Yeah, a sort of fat ring. His math showed this could drastically slash the exotic matter requirement. Suddenly, it wasn't planets or stars anymore. It was down to maybe the mass of the Voyager probe.
Voyager, that's like 700 kilograms.
Yeah. Exactly. Still exotic matter, mind you. Still negative energy, but an amount you could almost, imagine holding. Conceptually, at least.
That's a huge leap. So White wasn't just doing math, he was actually trying to test this, looking for that Chicago pile moment.
That was the goal.
Yeah.
A tiny flickering sign that you could warp space-time, even infinitesimally, in a lab. Like the first controlled nuclear reaction.
And they built a device, the White-Jude Warp Field Interferometer. Sounds fancy.
It does. The basic idea was clever, though. Use lasers, split a beam, send one part through a region where you're trying to create a tiny warp effect that used high-voltage capacitors for this.
Okay.
Then recombine the beams. If the space in that test region was warped, even slightly, the laser light passing through it would travel a slightly different distance.
And that would show up when you put the beams back together, like interference patterns.
Precisely. You'd look for a specific shift in the interference fringes when the device was powered on versus off.
And they found something. I remember the headlines back in 2013.
They did report something. A vanishing but non-zero difference was the careful wording.
Vanishing but non-zero. Sounds hopeful. The internet certainly thought warp drive was just around the corner.
The internet did. The broader scientific community. Let's just say they were significantly less impressed.
Why the skepticism?
Well, the reported effect was incredibly tiny, right at the edge of their detection limits. It was very difficult to rule out experimental errors, vibrations, thermal effects, computational glitches.
Mundane explanations.
Exactly. Plus, it didn't help that EagleWorks was also involved with other, let's say, controversial propulsion ideas at the time, like the EM drive. So there was already a layer of skepticism.
So inconclusive at best.
Pretty much. As physicist Sean Carroll put it, the chance of actual FTL travel happening in the next 100 years was probably less than 0.01%. That little flicker of proof still hasn't convincingly happened.
Okay. But let's imagine for a second they did solve the energy and the exotic matter problems. Let's say they built it. We're still not out of the woods, are we? The sources talk about even deeper problems, existential ones.
Oh, yeah. Building the drive might be the easy part compared to dealing with the consequences of using it.
First up, the horizon problem.
Right. If you're inside a bubble moving faster than light, you're causally disconnected from the front edge of your own bubble.
Meaning?
Meaning light signals, or any signal, from inside the bubble can't reach the front edge to tell it what to do. You, the captain, literally cannot steer. You can't slow down. You can't even turn the drive off.
So you're just a bullet, fired off and hoping for the best.
An uncontrollable bullet, yeah. You can't interact with your destination or change course until the bubble collapses, potentially way too late.
Okay, that's not ideal. What's next? The fry the destination problem. That sounds bad.
It is exactly as bad as it sounds. As this warp bubble speeds through space, it doesn't just push space aside, it scoops up any particles in its path. Interstellar dust, hydrogen atoms, stray photons.
It's like a cosmic snowplow.
A very effective one. And all that stuff gets piled up at the front edge of the bubble, getting blue shifted to incredibly high energies because of the speed and the space-time compression.
Oh.
Uh-oh is right, because when you eventually do manage to slow down or stop and the bubble dissipates, all that accumulated energy, potentially centuries worth of swept-up cosmic radiation and particles,
It's released.
gets released in a massive directed blast of high-energy radiation. Gamma rays, particle beams. The calculations suggest it would be powerful enough to, and I quote the sources, sterilize any planets at your destination.
Sterilized planet. So you arrive at Proxima B and accidentally vaporize it.
Pretty much. Your arrival is an extinction-level event. The Alcubierre Drive isn't just transport. It's potentially a weapon of mass destruction on an unimaginable scale.
Okay, that's horrifying. Surely that's the worst problem.
You'd think. But there's one more. The one that arguably breaks physics itself. Causality violation.
Time travel.
Time travel. Because in Einstein's spacetime, space and time are linked. If you can manipulate spacetime to go faster than light in space, the equations show you can also use it to travel backward in time.
Sending signals, or even yourself, into the past.
Yep, which completely shreds the concept of cause and effect. If effect can happen before its cause, then all of physics, all of logic, basically collapses.
I remember one physicist saying, if causality goes, physics might as well just pack up and go home.
It's that fundamental. It's why some physicists, like Stephen Hawking, proposed a chronology protection conjecture. The idea that the universe must have some unknown law that prevents FTL specifically to stop these paradoxes from happening.
Okay, so the original FTL Alcubierre Drive needs impossible energy, needs magic matter, makes you uncontrollable, destroys your destination, and breaks causality. Doesn't sound promising.
Not really, no. It's why it stayed mostly in the realm of science fiction.
But things have shifted recently, haven't they? Post-2020, there's been a sort of renaissance, but with a new rule.
A crucial new rule. No exotic matter. Physicists started asking, can we get any kind of warp effect using only normal matter and energy, stuff we actually understand? Forget FTL for a moment.
Was there a bit of a stir in 2021, someone claiming FTL without exotic matter? Lentz?
There was. Eric Lentz published a model claiming just that. It generated a lot of buzz, but also immediate pushback. The consensus growing now seems to be that FTL itself likely inherently requires violating those energy conditions. The universe really doesn't seem to want us breaking its ultimate speed limit.
But maybe FTL isn't the only point. Didn't another paper around then make a key distinction? Bobrick and Martyr?
Yes. That was arguably more profound in the long run. They showed that the need for negative energy, for exotic matter, seems to be tied specifically to going faster than light.
Ah, so if you're willing to stay below light speed.
Then maybe, just maybe, you can create a warp bubble using only positive energy. Normal physics, that's the critical insight.
And that led directly to this 2024 model, the one from Fuchs and Applied Physics, the Constant-Velocity Subluminal Warp Drive.
That's the one getting a lot of attention now. It's a warp drive solution derived entirely from general relativity using only standard matter and energy.
And crucially, it cannot break the speed of light. It's physically incapable of FTL.
Correct. It's sometimes called the physical warp drive because it sticks strictly to known physics. No magic required.
Okay, but then what's the point? If you can't go faster than light, why bother with a warp drive at all? Isn't that the whole dream?
That's what everyone asks. But the revolution isn't about top speed. It's about acceleration.
Acceleration? How so?
Think about space travel today, even just getting around the solar system. The big limiter isn't really the top speed our engines could eventually reach. It's how fast we can accelerate and decelerate without turning the crew into goo.
The G-force problem. Humans are fragile.
Very. A few Gs continuously is tough. High Gs for maneuvering are killers. But remember what's special about the inside of a warp bubble.
It's flat space-time. 0 G.
Exactly. Even if the bubble itself is being accelerated by some powerful conventional engine at, say, thousands of Gs.
The passengers inside feel absolutely nothing.
Nothing. They're still floating in zero-G, drinking their coffee. The drive isolates them from the inertia. That is the game changer.
Okay, wow. So you could use a powerful rocket to push this bubble, accelerating at insane rates, making sharp turns, and the crew would be totally fine.
That's the potential. It solves the G-force limitation. Suddenly, travel within the solar system looks radically different.
How different are we talking? Mars in months becomes.
Mars in potentially hours or maybe even minutes, depending on the engine pushing the bubble.
Yeah.
Years to Jupiter or Saturn become days or weeks.
That really does change things. Forget Interstellar for a moment. This
Right.
makes the solar system accessible.
It makes it feel small. That's the new, perhaps more realistic dream emerging from this research. The FTL Alcubierre Drive. Still seems like impossible fiction needs magic, breaks physics. But this subluminal physical warp drive, it's a brand new field, grounded in real physics, offering a path to truly mastering our own solar system.
So looking ahead, what are the predictions? Alcubierre himself seems pretty downbeat on FTL now.
Yeah, he's quoted as saying FTL is likely not for centuries, if at all. Sean Carroll still gives it that tiny 0.01% chance. Very skeptical.
But the new guys, Fruch and that group,
They're obviously much more optimistic about their subliminal approach. They argue this physical model genuinely changes the conversation about where propulsion research should focus.
it really does shift the perspective. Which leaves us with a final thought for you, the listener, to ponder. If we actually crack this subliminal warp drive, if we solve the problem of near-instant travel within the solar system, making Mars feel like a suburb and Jupiter a weekend trip, does chasing the FTL dream to reach other stars even matter as much anymore?
That's a good question.
If we can effectively turn our entire solar system into one vast interconnected city, maybe that's revolutionary enough for now. Something to think about anyway.